This is Dr. Reed and welcome to the Chapter 12 analysis video on regression. In this video, I will cover the following: purpose and assumptions of regression, simple regression, the end of the chapter exercise number 2 on page 382 using the home prices dataset, multiple regression, is your regression equation any good? And we'll end with a summary. The main purpose of regression is to predict a dependent variable based on values of one or more predictors, also known as independent variables. Simple regression models the relationship between a dependent variable and one predictor. Multiple regression models the relationship between a dependent variable and two or more predictors. Regression coefficients represent the slope of the regression line, or line of best fit, indicating the amount of change in the dependent variable for a 1-unit change in the predictor. Residuals are the difference between the observed values and predicted values. The smaller the residual, the more accurate the prediction. Now let's talk a little bit about some assumptions for regression. The first one is linearity. And we will be doing linear regression. And so there should be a linear relationship between the variables. And you can test this or examine this with scatter plots. Independence. The observations are independent of each other, meaning that each data point is based on a separate individual response. Homoscedasticity. Equal data spread around the regression line across all x values. N per predictor. For a reliable regression equation, you'll need at least 15 participants per predictor. Outliers. Outliers and influential data points are not overly influencing the model. I want to talk about that third assumption on the homoscedasticity in just a little bit more detail so that you can have a picture of what that looks like in your mind. So this picture here that you see on the right, this is a case where you see a scatter plot with a regression line or line of best fit in the middle, and you see that there's roughly equal spread of the data around that red regression line. So this is the case where you would meet that assumption of homoscedasticity. Here's a case, though, where you would not meet that assumption. So you have unequal spread of data points around the regression line across the x variable. And that would look something like this on the right. This would be heteroscedasticity. And you can see that down here in the lower part of the x variable, the data points are fairly close to the regression line. But as you move to higher values of x towards the right, the data points become more and more spread out around that red regression line. And this would be a case where you would be violating that assumption, and you would have to maybe collect more data or somehow look at the data to see if there's a way that you might be able to remedy this. And the reason why this is not good is because when you develop the regression equation for the data, it would mean that the predictive capability of the regression equation that you have is very good down here at the lower part, but it's not so good at the upper part of the x variable. And so you have sort of an uneven predictive capability of your regression equation. And that renders your regression equation not very useful in the real world. And so this is a case where you can see the homoscedasticity versus the heteroscedasticity. And the one you want to look for is the one up here in the upper right-hand corner. So let's start the end of chapter exercise number 2 on page 382. Okay, so what it's asking for is the home price data set. So this is a snapshot of the Jamovi ESCI where I loaded the home price data set into Jamovi. You can see that over here on the left. And we're going to use two variables for our simple regression. We're going to use the price variable as our dependent variable, and then we're going to use the size variable here as our independent or predictor variable. So we're trying to model the relationship between the size of the home in meters squared versus the price of the home. And we're going to try to develop a regression equation from that. So the way you'd go about doing that is you click on ESCI, and then with the pull down menu, oh, I'm sorry, one other thing about the database over here, there's 300 cases, and that's good because as mentioned in the assumptions, you need at least 15 cases or 15 participants per predictor variable. Well, in this case, since we only have one predictor variable, we have ample number of cases. We have 300, so we're clearly okay as far as that assumption. So then you go to ESCI and do the click on ESCI, and then go down and select correlations single group, and from there we can get the regression. And so you bring the price variable over to the y variable and bring the size variable to the x variable. And then go down below and you see there's some tick boxes that you can check. And basically you can just check the regression analysis. And then you also see down below here there are other boxes you can check. You can ask ESCI to give you the line on the scatter plot, the confidence interval on the line, etc. So there's lots of extra things that it can do. Once you do that, then you'll get the results over in the right panel over here on the right. And I'm using those for our presentation so we can answer the questions for the end of chapter exercise. So here's the description of the end of chapter exercise. You're thinking about buying a house in California. Regression can help you. Using the home prices data set, explore the extent to which the size of the home in meters squared predicts the sales price. The file contains real estate listings from 1997 to 2003 in a city in California. Letter A, create a scatter plot of the relationship between home size, X, and asking price, Y. Does the data set seem suitable for regression? What is the R, or correlation, between home size and asking price? So here is the scatter plot of that. If you look over here on the right, so you can see that we have price on the y-axis, and price is the dependent predicted or criterion variable, And size down on the x-axis, the size of the house, is the independent or predictor variable. And if you look at the shape of the scatter plot in terms of just kind of the general shape of the data points on the plot, we have this kind of an elliptical pattern that runs from the lower left to the upper right. And this would indicate a positive relationship between size of the house and the price of the house. That is, there's a general tendency, which you would expect, there's a general tendency for, as the size of the house gets larger, the price of the house becomes more. So this is the general relationship that we have. And then there's the line of best fit, that blue solid diagonal line that you see that runs right through the data points on the scatter plot. The computer generates this, and they call it the line of best fit or the regression line because it's the line that essentially minimizes the error between the line and the data points on average in terms of the entire scatter plot. So it kind of fits the line in terms of the best predictive capability for your regression model. So they're asking for what is the R between home size and asking price. So I have that up here. We have an R, or Pearson correlation, of 0.78. And as a reminder or review, the correlation, the range of the values possible for a correlation range from a -1 through 0 to a +1. 0 indicating no relationship whatsoever between the two. So here we have a fairly strong positive relationship between size of the home and the price of the home, which again, you would probably expect. If we square that correlation, we get the coefficient of determination. So 0.78 squared is 0.61, and if we multiply 0.61 times 100, you get the percent of shared variability between the two variables. So in this case, we have where the about 61% of the variability in price is accounted for by variability in the size of the home. So it's not a direct perfect relationship, and the reason why is as the size goes up, the price goes up. But there are other factors that go into having the price be higher or lower than just the size of the house. For example, like the condition of the house. We're only looking at one of the possible factors that affect price. But in this case, in this context, with this data set, we see that about 61% of the variability in price is accounted for by variability in the size of the home. So yes, the size of the home does have an influence on the price. And then there's the R 95% confidence interval ranging from about 0.73 to 0.82. So again, this is our range of plausible values in the population that we believe are there for our point estimate of 0.78. So one of the next letter that I chose for the presentation for the exercise is letter C. What is the regression equation for predicting price from home size? So again, one of the main purposes, if not the main purpose of regression, is to develop a regression equation for prediction. And so I copied the output from the ESCI, and you see that over here on the right. So you're given a component, the intercept and the slope, the value of those two, and the confidence interval for each of those two. So for a straight line in a linear situation, those are the only two components you need. you need the intercept and the slope. So the intercept in this case is a minus $66,024. Now, by definition, the intercept is the value of y on the vertical when the x value is 0. So think in your mind, that line on that regression scatter plot, it would move down and would intercept or cross over the y-axis at about a minus 66,000 if we brought x all the way down to 0. Okay, so this component is needed for the equation in terms of prediction, but it doesn't have any, we're not really interested in that intercept in this case, because, well, first of all, there's no house that has a square footage of 0, right? So that we have no interest in that in our equation, other than it has to be there so that we can obtain our mathematical prediction from the equation. So we are much more interested then in the slope here of the regression line. Okay, and by definition, that slope then is the change in the price for a 1 unit change in the meters squared. So for every increase in meters squared, there's an increase in the price of about $2,700. So there's the equation right there that they put at the bottom, and we will use that as our answer for letter C over here. So that's the equation right there. Y hat, the little caret on top, Y predicted is equal to minus 66,024 plus 2713 times our x value. So the name of the game here is to then be able to plug in an x value here, do the math, and obtain the predicted value over here. So you can see the math is very simple there. So let's do an example. So I chose letter F here for this one. If a house has a size of 400 meters squared, and by the way, I think I changed the value that they used in the textbook for letter F. I think I changed that to something that was better in terms of an example, I thought. So we're going to go with 400. So if a house has a size of 400 meters squared, what is the predicted asking price? So all you do is just plug the 400 meters squared into the equation as your x value and solve for y. So let's do that. So there's your answer right there. The predicted price for this data set is about $1 million. $1,019,176 is the predicted price based on the data set for a house of size 400 meters squared. And so I believe I have a picture of that over here on the right. So let's take a look at that now. So there's the same scatter plot that we had before, and ESCI will give you this information that you see in red. So there's our x of 400 down here on the x-axis. And what we do is the equation then, when you plug in an x value, any x value, into that equation, the answer that you get from that equation is going to be on this line here. So every single value down here that you plug in any value down here. Any value that you plug in down here, the predicted value that you get will be a value that corresponds to being on that line. So for this example, we have x is 400, and we plug it into the equation. We go to the line, there's our point, and then you just follow that over to where it intersects with the y-axis, and you get your answer, which is right there. Now, as you can see, the software is getting a slightly different answer than what we calculated over here, but it's pretty close. We calculated an answer of 1,019,176, and ESCI calculated an answer of 1,019,325. So it's definitely close enough. So there's your picture of what we did over here on the left. So to repeat, the equation predicts the mean value of y for a specific x value, and that mean y value is always on the line of best fit. Very important. Let's move on to letter G now. So letter G asks, how well can we predict the mean price for houses of 400 meters squared? So to answer this, you need to obtain the 95% confidence interval for that predicted value. And the ESCI will give us that too. So in other words, when you plug in an x value into the equation, you get a y value. That's sort of like a point estimate for our prediction. Well, we want to keep in tune with the purpose of the textbook. We want to make sure that we have a confidence interval around that predicted value, so that we can make a judgment as to how accurate that prediction is. So I just took that from the output, and then I'll also give you a picture of it. So here is the 95% confidence interval for that mean y predicted value when x is 400. So the lower limit is 958,500. There's our point estimate, and the upper limit is 1,080,140. All right. And so to get an idea of the margin of error there, you would just subtract the PE from the upper limit or the lower limit from the PE, so you can get an idea for the margin of error. And if you round up our PE to the last part, we have 1,019,176. So if you just round that up to 20,000, and then round the upper limit, the 80,140 down to 80,000, you can see that our margin of error, or MO, is about 60,000, which seems to be fairly reasonable. Let's take a look at a picture of that now. So here's the exact same scatter plot again, with two added pieces. Number one, this small little red band around the point estimate for our prediction. Right? That right there, that's the confidence interval that you see over here on the left. Okay? The other thing that you see on this scatter plot that was not shown before is the light blue shaded area around the dark blue regression line. And what that is essentially the confidence interval around the regression line for all points of x. So all the way across the x variable, we can get a sort of a prediction, 95% confidence interval band around the regression line. And so if you look at the lower portion of the scatter plot and regression, you notice the distance here, or how kind of tight that band is around the regression line. But as you move up towards the higher end of the regression up here, you can see that that band starts to widen a little bit. And that means that the predictive capability here is a little bit less accurate on the upper end than it is on the lower end. Part of that is because if you look up here, there's not as many data points up here. So the data seems to be concentrated down on the lower side here. And so that's part of the reason that we see change, that the band is not necessarily even. Of the light blue shading band is not necessarily even across the entire range of the regression line. Let me zoom in now on that confidence interval so you can see a little more detail. So there I've zoomed in. I took a picture of it and added some information. So there's the same information there. There's the lower end of the confidence interval. There's the upper end of the confidence interval. And then I drew a line across to the corresponding Y value. So there's the lower confidence interval value and the upper confidence interval value, which are the same values that we have down below here. So that's a zoomed in picture of this mean Y predicted value and its confidence interval. So we also have the case where the book talks a little bit about if you have a slightly different purpose for your regression, what kinds of statistics you should get in order to be able to summarize the purpose that you have. So the first one is you might be interested in the population level relationship between X and Y only, rather than just prediction per se. So in order, what you should do there to do is you need to compute the R and the R 95% confidence interval. Then also the regression equation and the regression coefficient slope 95% confidence interval. So those are the things, if you're just interested in the population level relationship between those two variables, you're not interested in predicting, you should just compute R and its confidence interval, and then also the regression equation and focus on the coefficient and its 95% confidence interval. Now that coefficient relies on the assumption that you have random sampling of Y from a normally distributed population with homogeneous variance across all X, i.e. homoscedasticity. And then the second thing would be what we've already talked about. You want to predict the mean value of Y for all participants with a value of X. So to do, you would use the equation to find the point estimate of the mean Y at X, that is, find Y hat at X, and then compute the predicted Y 95% confidence interval. A third thing that you might be interested in is if you were to sample a new participant with a particular X score, what would their Y value be? To do, compute the prediction interval for Y values at the X value. The PI is the range of Y values that is likely to contain the Y for the new observation at X. PIs are wider than the mean Y 95% confidence interval because they must account for the uncertainty in estimating the mean Y at X and for the spread of the individual Y values. Now, that being said, the main thing again is number 2. Regression is mainly used for prediction. Let's move on now to multiple regression. We'll give you a couple of examples there. Talk about the simple versus multiple regression equation. And then talk about the important point of how do you interpret the multiple regression coefficients. The best way to do that is with what's called semi-partial correlations. And we'll end up with talking about the assumptions and then an issue that is it's an additional issue with multiple regression that you don't have with simple regression. So here's a couple of examples. Agriculture researchers might use different fertilizers and water on different fields to examine how the variables affect crop yields. The model might look like this. So you're trying to predict crop yield, and then I'm using the terminology here. This is the coefficient. Those B's are the coefficients. So B sub naught is just the y-intercept. And the model then might have as the first, we have a B1 coefficient, and then the fertilizer brand, and a B2, the amount of water. So the idea here might be to have several different equations or one large data set that has codes for different types of fertilizer brands and different amounts of water to see which combination of fertilizer brand and water would yield the best crops. Another example might be in the medical field. Medical researchers may administer doses of a drug and observe blood pressure response. They must consider other variables related to blood pressure, such as age, gender, and body mass index. The model might look like this. So you're trying to predict blood pressure response based on dosages of a drug. So your first variable might be the different types of dosages for the drugs. Second one might be the different ages that are involved, because maybe people of different ages respond differently to the drug. The third variable might be gender, and the fourth variable might be the person's body mass index. And so we're trying to find the best combination or combinations for these variables to predict blood pressure. And then the last example I have would be in the insurance industry. So insurance researchers want to know predictors of car accidents, so insurance payouts can be budgeted efficiently. The model might look like, here you have the probability or risk of accident as the dependent variable, and then you might have the value or the Blue Book value of the car as a variable, the person's age as a variable, the age of the car, the car color might go into play. So the idea with all three of these examples is that usually in a real life situation, there's usually more than one variable that will be involved in giving you the best prediction for an outcome. That being said, if you decide to do a regression analysis for your dissertation, your predictor variables should be based on the literature and existing theory. So let's take a look at the difference between the simple and multiple regression equations. So for simple regression, as mentioned, you just have your y variable, and then this here is the y-intercept, the b sub naught, b sub 0. And then you just have one predictor variable here. That would be the x, so x1, and then the b1 is the coefficient for that x, indicating the slope of the line for that x variable. And it also indicates the coefficient b1 indicates because it's the slope, it's the change in y for a 1 unit change in x. And b is calculated using a Pearson R. In multiple regression, it's just an extension of the simple. You have your y predicted, your y-intercept, and then you just have b1x1 plus b2x2 plus b3x3. So here we have more than one predictor. The procedure for the multiple regression finds variables that work best together to predict y, and then computes the coefficients for each variable. So the B's estimate the population slope between y and x for each variable, and then as before, they indicate the change in y for a 1 unit change in x. So in multiple regression, you're interested in the contribution of each x in explaining y variability or variance. However, the x's often correlate with each other. And that shared variability between the x's must be partialed out of each x. So you can quantify the unique contribution of each x to explaining the y variance. So there's a little bit of a complication here with multiple regression because the x's are correlated with each other. And we're not interested in that. We're interested in how each x correlates with y. And so we have to come up with a procedure that'll allow us to kind of get rid of some of the shared variability between each of the x's so we can get the part of each x that only correlates with y so that we get the unique contribution of each x to explaining y variance. And for that, we enter the semi-partial R. That's exactly what a semi-partial R will do for you. So for multiple regression, it's useful to interpret the regression coefficients, or B's, as semi-partial correlations, which you can do. A semi-partial R is the correlation of y with the part of x that is independent of its shared variability with any of the other x's. In this way, the semi-partial R quantifies the unique contribution of the x variable to explaining y variance and tells you how important that x variable is in predicting y, while holding the effect of all other x variables constant. So in the output for a multiple regression, you can get the equation, but you can also have the computer give you the semi-partial R's for each of the betas, or each of the B values, or coefficients. And so you can interpret those coefficients as semi-partial R's as a way of interpreting what you have in terms of your regression equation. So I'm going to give you an example of that, sort of a schematic example. So multiple regression conceptualized with semi-partials. So I'm going to use the example where there's 3 predictor variables, but for each of those equations, I'm not going to put the y-intercept or the constant in those equations. So let's take a look at the first one. So essentially then you can replace those coefficients with the semi-partial R's as a means or a way of interpreting your regression equation. So, for example, we have the y predicted, that's the same as before, and that would be equal to the whatever that first B coefficient was, we can, in its place, put the semi-partial R for that one, and that would be this one right here. So you look at this, and we have the R, Pearson R correlation, and then there's the little the way it's named here, you can see sort of a subscript. And so let's interpret that. So what that subscript is telling you is that R is the correlation. So this is the correlation between Y and the first variable in the equation, where the influence or shared variability of variables 2 and 3 have been partialed out of the first variable. The second one could be or would be interpreted as the correlation between Y and the second variable, where the shared variability of variable 1 and 3 has been partialed out of that second variable. And the third one is the correlation between Y and the third variable, where the shared variability partialed out of the third variable. Now, as with Pearson R, if you square the semi-partials, you get the percent of Y variance explained, which would be sort of your endpoint of your interpretation here. So all I'm going to do now is do exactly the same thing I did before and just square those, and we can interpret them accordingly. So the first one is the following, because it's R squared. It's the percent of variance explained by X1, this percent of Y variance explained by X1 with the shared variance of X2 and X3 partialed out of X1. And the second one is the percent of Y variance explained by X2 with the shared variance of X1 and X3 partialed out of X2. And finally, the third one would be the percent of Y variance explained by X3 with the shared variance of X1 and X2 partialed out of 3. So what that does is it gives you then for each of the 3 variables that you have in your equation, gives you the unique contribution of each variable without the influence of any of the other variables, okay? Gives you the unique contribution of each variable to explaining some of the Y variability, because that's what you want. It's called a semi-partial correlation. What we're talking about now is not, we're talking about the way to interpret the multiple regression model or multiple regression equation that you have. This is a way to interpret it, which is usually the hardest part. So let's move on now. So then the final thing here is the assumptions and issues that would be involved with multiple regression. First of all, the assumptions are the same for multiple regression, basically, as they are with the simple regression. Linearity, independence of observations, the homoscedasticity, the n per predictor, and outliers. And then there's one additional important issue that comes up with multiple regression, and I talked about it just prior on the last couple slides, and that has to do with the notion that those X variables are correlated with each other. That creates a kind of a problem. And the issue here is called multicollinearity. So in this case, the predictors are often correlated quite a bit with each other. And they're correlated with each other to the extent that the software cannot separate them out. In other words, the variables you have, they're so correlated with each other, the computer program can't determine if there's more than one variable there, because they're so alike. It's as if there's just one variable. So that's a problem. Okay. So you would want to test for that multicollinearity. And there's various ways to do that. One test for multicollinearity is an index called the variance inflation factor, the VIF, and you can get that with the output very easily. And all you have to do is just look at it. And if the VIF values are close to 10 or above, that would probably signal a multicollinearity problem. So for each variable in your regression model, you can get a VIF value. So any variable that has a VIF that would be close to 10 or above means that that variable is correlated with very highly with at least one other variable in your model. And so you would need to look at that to see if you could remedy the situation. So here's a couple of solutions. One thing you could do would be to simply remove the variables that are highly correlated. That's one thing. The other thing you could do would be to combine the highly correlated variables that are similar in concept into single variables. So let's say, for example, you have 4 variables and you discover that variables 1 and 2 are highly correlated with each other, but they also kind of measure something that's very similar. And then you find out that variables 3 and 4 are highly correlated with each other, but they also, those variables 3 and 4 measure something that is similar. So what you could do is combine variables 1 and 2 into a single variable and combine variables 3 and 4 into a single variable. And there are various ways of doing that. So instead of having 4 variables, you just reduce it to 2 variables now that are not like each other. And now you can run your regression on that one. So just this slide again, assumptions and issues with the multiple regression. The assumptions are the same, but one additional issue that pops up all the time is this multicollinearity, and you have to kind of deal with that as you proceed. And the last slide then is ways of looking at, is the regression model or equation you have, is it any good? One thing about doing a regression for your dissertation that's kind of nice is you're actually developing something that someone can use. So if you develop a regression equation on some data that you collected, then the idea is that other researchers could use your equation if they only have access to X values, but they don't really have the time or they don't have access to the thing that your model predicts. Well, they could just plug in their X information into your equation and predict what that thing would be without even having the Y information. So in a way, you're kind of developing sort of a product that a tool that other researchers can use to make predictions. And in order for you to say that that is a good tool, you have to be able to have a way of maybe looking at that to see if it's any good. So there's several ways to do that, and I'll give you 2 of them here. So you want to look at least 2 things. First would be just simply the R squared or R squared. So notice here I have a capital R here and a lowercase here. So the capital R would be for a multiple regression where you have more than one independent variable. And then the little r squared would be for a simple regression where there's just one predictor. Okay? So you can get sort of this. So if you look at this in terms of the multiple regression, you can get an R squared that's like a global R squared for the entire model. Okay? And so that R squared tells you the percent of the total variability in Y that is accounted for by the prediction model or your prediction equation. The larger the better. but it depends on the situation and the quality of the measurements. So for example, in psychology and education, R squared of 0.5 to 0.75 is pretty good. But in fields like physics and chemistry, you might be expecting R squared, say, 0.9 or greater. So the R squared, again, is sort of context bound here. The second thing you can look at is the standard error of the estimate. The standard error of the estimate. Okay, and the standard error of the estimate is essentially the standard deviation of the y-scores around the regression line at the population level, supposedly. Okay, it's the standard deviation of the y-scores around the regression line, which, in a sense, is depicting the standard deviation of those residuals, which is the difference between the y-scores that were observed and the actual prediction line. Okay, and in this case, the smaller the better, right? The smaller the better. And I'm just showing you how that's calculated there. There's 3 different ways to compute it. The computer gives it to you automatically. So you would look for the standard error of the estimate. And it's, again, the standard deviation of the y-scores around the regression line. So that would be equal to this. Okay, each y minus the predicted value squared divided by n minus 2 in this case. And then you take the square root of that. So this is essentially the formula for a standard deviation right here. Or the computer calculates it by looking at the sum of the squares error output divided by n minus 2, and you take the square root of that. Or a pretty simple way to do it is that can be done by hand is that if you have the standard deviation of the y-scores, you would just take that times the square root of 1 minus r squared, or big R squared here too. It could be either one. All 3 of those will give you the exact same result. So if you use those 2 together, they kind of complement each other so you can make a determination for the quality of the regression equation that you developed. Okay, so the R squared measures the proportion or percent of y variance explained by the model, i.e. the equation, and the SEE provides an absolute measure of the prediction error for your equation. So let's summarize. Number 1, the main purpose of regression is prediction. The assumptions: linearity, independence of observations, homoscedasticity, n per predictor. Remember, you need about 15 people or values for each independent variable that you have, and outliers. The equation that you develop predicts the mean y for a specific x, and that mean y value is always on the line of best fit. Your predictor variables should be based on literature and existing theory. In multiple regression, it's useful to interpret the coefficients as semi-partial correlations. Multicollinearity is a common issue in multiple regression. And finally, you should always check the regression equation for accuracy. And for starters, use R squared and the standard error of the estimate as first line checks. So that takes care of the chapter 12 analysis video on regression. There's a 5-point quiz on that. If you have any questions about it, please send me an email. Thank you for watching.